One of the main reasons why life is made out of carbon, mostly carbon, hydrogen, oxygen, but the structures are mostly made out of carbon, is because carbon is one of the most unique elements because it can form single bonds to themselves, so single bonds to other carbons and single bonds to hydrogens. This explains why carbons can form long chains of carbon and hydrogen. And in this video, we're going to talk about what those long chains look like and why is it that carbon can form those long chains. So in the previous videos, we were doing the Lewis representation of simple molecules, in this case for methane. Methane means one carbon. Just for the record, you will have to memorize this. Methane is one carbon, ethane means two carbons, propane means three carbons, butane means four, pentane means five, and hexane means six. That's as much as organic nomenclature that we may ask you to remember at this point. The met, eth, prop, but, pent, and x, that means 1, 2, 3, 4, 5, 6. And the fact that it's ane, it's because it's an alkane. Okay, so you will see how systematic the nomenclature in organic chemistry can be. So what is the Lewis structure of methane? Notice that the formula for all these compounds will always follow this trend in which for you have CH4 because N is equal to 1, right? So if N is equal to 1, 2 times 1 is 2, 2 plus 2, 4. What is when N equal to 2? When you have two carbons, what is the formula of alkanes? So now you have two carbons and you have how many hydrogens? 2 times 2, 4 plus 2, 6. What is when N equals 3? You have three carbons. How many hydrogens you have? 2 times 3, 6 plus 2, 8. All right, and as we have said here, this is methane, ethane, and propane. So let's see what they actually look like. The Lewis structure of methane is this one that you see here. Carbon needs to follow the octet rule, and so this is what methane looks like. Notice that instead of hydrogen, you can attach a carbon in there, and then you have ethane. So ethane is a chain of two carbons. So carbon-carbon is bound, and now this is ethane. What does propane look like? Well, now it's three carbons. So hopefully three carbons aligned. You have three carbons in here, and now you need to fill up the valence with hydrogens. So let's check, is this so far following the rule? In here I said that propane should have 8 hydrogens. Does it have 8 hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it follows the rule. Butane, 4 carbons. So let me put the 4 carbons first. So far I'm putting them in a line. You'll see in the next slide that that may not be the case. So let me fill the valence, because all the carbons need to follow the octet rule with hydrogens. Okay, how many hydrogens should I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the rule should be 2n plus 2, so 2 times 4, 8 plus 2. It's a 10 that I was expecting. Good. So pentane. 1, 2, 3, 4, and 5. So you will see that as I'm writing this, it becomes kind of tedious to write all these hydrogens. It's a lot of writing. And in organic chemistry, one needs to write these structures quite often. So finally, hexane. So on the right side of this slide, you will see that there's something called skeletal representation. And the skeletal representation is a way to simplify these structures because it takes a long time. If I were to draw a chain of 7 or 10 carbons, you can imagine the time that it takes. My hydrogens stop looking like hydrogens even, so careful with that. All right, so these are the structures for hexane, pentane, butane, propane, ethane, and methane. What is the skeletal representation? Well, maybe because we know that the composition is only carbon and hydrogen, we don't need to write them all. We can simplify. For example, for propane, in here has 3 carbons. So I'm just going to say 1, 2, 3. So that would be 1 carbon, 2 carbons, 3 carbons. That's it. I don't need to write the hydrogens because it is assumed. What would butane look like? So 1, 2, 3, 4. 1 carbon, 2 carbons, 3 carbons, and 4 carbons. That is the representation of carbons, of butane in this case. The representation of pentane. 1, 2, 3, 4, 5. That's it. What is the representation of hexane? 1, 2, 3, 4, 5, 6. Okay, so it's much, much faster. For ethane, you would be maybe drawing a line representing the 2 carbons with the hydrogens attached. And methane, no one would ever really draw a point. Okay, so that the skeletal representation in which the hydrogens are implicit is only useful when you start drawing longer chains. So let's just do a simple exercise in which in here it's asking how many different compounds can you build with 4 carbons. Understood that it's alkanes. Well, in the previous slide, we have drawn the butane, right? That is my butane. So can I draw a different one? So in here, it may be useful to draw the explicit representation. This is my butane. And notice that it's all single bonds with no lone pairs. So if you like to play Legos, this is going to look like a Lego game. Notice that here, this CH3 on one end can go in here. So what would that look like? Well, it still has 4 carbons, but now I'm attaching one here. Okay, and now I saturate the rest with hydrogens. Always make sure that all the carbons follow the octet rule. Okay, so in other words, you have butane, the one on the left, and this one, which is called N-butane, sorry, isobutane. Oh, so we are removing this one, so, and instead of adding this one here, I'm adding one on top. Okay, so there are 2 different compounds for having 4 carbons. How many compounds there are with 5 carbons? In here, it may take you a while then to realize, but this is my, let's count, 1, 2, 3, 4, 5 carbons. Yep, that's the one I drew before. Now, I can place this one on closer to the chain. So I stop here and I add the next one here. Okay. Now, another one. Maybe I can take the other end and add it on this side. So, and this is going to be, wow. Okay, what would that look like? In here you have CH3, 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 and finally CH3. Notice that it still follows the same rule that the C5H10, no, H12, sorry, right? It should be 2 times 5 plus 2 is 12. Do I have 12 hydrogens everywhere? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that is true. The longer your chain is, the more different compounds you will be able to draw. Notice at some point you're going to need models because it's probably very hard to picture this. All right, so we will definitely practice in class. Bring your models to class and hopefully this will make some sense.